Everybody now know where you're supposed to go on Tuesdays? Discussion class? Anybody is still not knowing this, see me for a moment after our chat. I'll make sure you are informed of the correct location. All right, before we proceed with chapter 17, as to this tail end of our last talk, I do stuff like this to start at 2046 simply because, as we've already reminded you, structure is the most important property of any species. If, for example, you're curious about the polarity of this mountain, you have to know what structure. And when I say structure, that also means shape. It's not just bond sites, position of the bond, central atom versus peripheral. Important. That's why I also said if you need to review the rules of the road for making Lewis structures, it's all in chapter 23 of our notes. Now then, from a theoretical standpoint, because I expect that when you learned about this stuff in 2045, before you talked about the shape of the molecule, you talked about the in-space distribution of the valence electrons associated with the central atom. SP, linear, 180-degree angle between these valence electrons, or valence electrons. SP2, how many electron pairs? 3. Do you remember that the compositional nature of a hybrid tells you for an even electron species? What's that mean? Even electron species. Remember seeing this term in the discussion for assignment 6, 2045? Which was all about Tinker Toys, making models. Even electron species is a species with a sum total of valence electrons that's an even number. That's all. For an even electron, sp hybridized central atom. How many valence electron pairs in the valence environment of the central atom? That are sigma. A bunch of language you have to learn. Because you also learned in playing this game that at bond sites, besides sigma electron pairs, you might also find what kind of electron pair? Pi. Now, pi electron pairs in general certainly affect bond strength and bond length. But don't exert effect on molecular shape. That's really not true. Because if you change the length of the bond, you're affecting molecular shape. But sigma electron pairs, particularly for central atoms, are the principal shape-determining properties of the species. sp hybridization. 180-degree bond length. How many sigma electron pairs? What I was going to say a moment ago is that the nature of the hybrid tells you how many sigma electron pairs are in the valence environment of the central atom for an even electron species. Again, even electron species means the sum total of valence electrons for the atom in question is an even number. sp hybrid. How many orbitals are ground up, mushed together, mixed, or to use the fancy word, hybridized? How many orbitals are mixed up to make an sp hybrid? 2, S and P. Did you learn that making hybrid orbitals is like making sausage in the meat market? It is. Butcher's making 2 pounds of sausage, 50% beef, 50% pork in character. Meat grinder, 1 pound of beef, 1 pound of pork, perfect grade. How many pounds of sausage do I get out? 2. Well, what I get out is no longer pure beef or pure pork. 50% beef in character, 50% pork in character, isn't it? Well, now let's make sp hybrids. S orbital, p orbital, now I have an orbital grinder, not a meat grinder. Turn the crank. I put in 2 orbitals, so I get out 2 orbitals. And each one bears the label sp. Because each one is now 50% S in character, and 50% P in character. You didn't play this game, see? How many orbitals did I hybridize? 2. How many electron pairs can I put in an orbital? Electron pairs in an orbital. 1. Because an orbital electron capacity is 0 unoccupied. 1 electron half filled, you're dealing with a radical, or an electron pair, which is the most common occupancy for an occupied orbital. So sp hybrid, 2 sigma valence electron pairs. sp2, how many orbitals am I hybridizing now? 3. So if it's an even electron species, I have 3 sigma valence electron pairs. And based on valence shell electron pair repulsion, you all heard about that. Do you know what it means? It means coulombically. If you take a collection of sigma electron pairs and put them in the valence shell of an atom, the electron pairs are constrained to remain in the valence shell. They have to stay in the valence shell. But while in the valence shell, they are imagined to scramble about, staying in the valence shell, so as to assume positions, geometric positions, which minimizes the overall degree of repulsion among and between this count of valence electron pairs. sp2, that's 3 sigma valence electron pairs. What kind of general geometry do you get from the electron pairs? Trigonal plane. Now then, you know that any 3 points in space are containable in a plane. So when you got 3 sigma electron pairs, those are the 3 points. So you can use the clock. Little analog clock. This digital stuff is great, but it causes us to lose a lot. People who insist on doing arithmetic strictly with calculators are usually lousy at arithmetic. Because the calculator does the arithmetic. Not the best computer you have by far, which is this thing. That's what you should do arithmetic with, always. And you can finalize the calculation with your push button device. Okay? The nucleus of the central atom is the center of the clock, the pivot point, or the hour, minute, and second hand. Okay? So pick a reference point. Of my 3 sigma electron pairs for this sp2 hybridization, I'll put 1 electron pair at high noon. So let's imagine all 3 of the electron pairs start at high noon. 1 stays at high noon. The other 2 scramble about in this valence shell. What positions do they assume with respect to the clock numbers? 8 o'clock and 4 o'clock. So if I draw a line from noon to the center of the clock, and another line to 8 o'clock, and another line to 4 o'clock, I've taken a pie and cut it into 3 equal pieces of exactly the same shape. And if I get out my protractor, or whatever you want, and measure the bond angles, it's 120 degrees. SP3, now you have to be a little bit more clever. Because you get to SP3 hybridization, you have to recognize that this valence shell is spherical. It's not flat. If the valence shell was flat, SP3 hybridization, how many sigma electron pairs are we talking about now? 4. If the valence shell was flat, but atoms ain't flat, are they? And only instructors of chemistry and emperors of Byzantium and empresses of Byzantium, they use the word ain't. Any emperors or empresses of Byzantium in here? Well, then you're disenfranchised from saying ain't. Only I can say ain't. 2 years ago, I mean, I stand up. Said it's from Byzantium. If the valence shell was flat, you recognize you get a square shape. Electron pair, electron pair, electron pair, electron pair. And the bond angle would be all exactly how much? 90 degrees. Aha! That valence shell ain't flat. It's spherical. And if I recognize that with a sphere, I can get these 4 electron pairs for sp3 hybridization for the central atom to be scrambled about in the valence shell such that the bond angles among and between these electron pairs is a lot bigger than 90 degrees. What is the bond angle? 109.45 if I take it to the hundredths place. Because you have an electron pair here, an electron pair here, an electron pair here, an electron pair here. If this valence shell was square, but it isn't square. So let's keep this electron pair here and this electron pair here and take these 2 bottom electron pairs and do this. I rotate them 90 degrees with respect to the top electron pair. What shape do I now have? Tetrahedron. Both got the bond angle of 109.45. That's the way you get all these shapes. That's the way games like this. What hybridization applies to the central atom nitrogen? Now, you've got to be a little bit more flexible in your thinking to analyze this problem because this ain't an even electron species, is it? Got 17 valence electrons. How many valence electrons? Sigma valence electrons in the valence environment for nitrogen central atom here. Sigma valence electrons. How many? You're looking at the picture. All you got to do is look at the picture. You made the picture correctly. You can always determine the number of sigma electrons or electron pairs in the valence environment for any central atom for which you've made the Lewis structure correctly. Now, to play this game, you've got to know another rule. If the central atom has 1 or more non-bonding electron pairs, how are they counted? Are they counted as sigma? Is hybridization applied to these non-bonding electron pairs? Like these 2 central atom non-bonding electron pairs for the water molecule? Do these non-bonding electron pairs count as part of the sigma framework? Yes or no?
Yes.
This is simple Lewis structure stuff, simple valence bond theory. Are these to be considered as sigma electron pairs, yes or no? The answer is, how's this oxygen hybridized? sp3, 1, 2, 3, 4 sigma electron pairs, non-bonding electron pairs, and single non-bonding electrons are part of the sigma system. The geometry for the species will tell you this. So if you didn't know what the question, if you didn't know the answer to the question, you would, if you could, take this molecule to the laboratory and make bond angle measurements. When you found out the bond angle for this was on the order of 105 degrees, you recognize sp3 hybridization. Bond angle somewhat less than 109.45 degrees, because non-bonding pair, non-bonding pair, bonding pair repulsion exceeds bond pair repulsion, when at the bond sites you have only a single pair of electrons. All this stuff, 2045. Something neat to know. So I repeat my question. How many sigma electrons for this cyclogram? I heard 3. That's not right. 5. At each and every bond site, there is always one and only one sigma electron pair. There's even exceptions to that. But I'm not going to talk to you about sandwich compounds at this stage. We'll wait 2 weeks for that. A sigma electron pair and a pi electron pair. And this is a non-bonding electron. Is it or is it not sigma? Is it or is it not sigma? It is. So the hybridization for this thing is what? Because I got to have 1, 2, 3 sigma orbitals for these sigma electrons to live in. One pair, another pair, and a one single electron. Well, how's it hybridized? And bond angles, pardon me, electron pair angles associated with sp2 hybridization we just talked about. 120 degrees. sp3 hybridization. Electron pair angles. 109.45. Well, this isn't 109.45 angle. Now you've got to pay attention to the difference in repulsion between bonding electron pairs versus non-bonding bonding electron pairs. So finally we get back to this. What are you talking about bond angle molecule? Do you expect it to be perfectly 120 degrees? I should hope not. So the question is this bond angle bigger or smaller than 120 degrees? Let's have a vote. The bond angle is bigger than 120 degrees. No looking around. I run this election. If there's any cheating or crookedness, it's because of me. Any corruption is attributable to me. Smaller than 120 degrees. How many didn't vote? Those who didn't vote, 1,000 points off quiz 1. And you didn't even get quiz 1 yet. See the penalties you get if you don't? Two non-bonding pairs. A single non-bonding electron. Do you think a single non-bonding electron will exert as much repulsion on the bonding electrons as two non-bonding electron pairs? Huh? Hell no. And here at the bond sites, how many bonding electrons do you really have at these bond sites? Be careful when you answer this question. The number of bonding electrons at the bond sites is easy. That's 6. 3 bonding electron pairs total. But at a given bond site, this bond site or this bond site, or this molecule, at a given bond site, from a number standpoint, how many bonding electrons? Or let's ask it this way. What's the bond order? The NO bond order. You heard about bond order in 2045, did you? NO bond order. Numerical value for the NO bond order. What is it? What is it? 1.5 or 3 next. Same thing. 1.5. Because this molecule shows what very important valence electron property? R-E-S-O-N. Resonance! Right? But you now have a greater degree of repulsion between the bonding electrons than you do here, because here the bonding electron density is greater, and the non-bonding electron density is far less than what you have here, which accounts for why the observed bond angle for this thing is 134 degrees, which is a pretty good deal larger than 120. How about that? Now, from this simple analysis, there's no way you could get at prediction of the actual bond angle, but you should be able to predict that it's bigger than 120 degrees, for the reasons we focused on. Now let's get back to chapter 17. Chapter 17 concludes with an analysis of problem 17.1, challenge problem. And the main contention of our analyzing this challenge problem is to make you aware of a problem-solving consideration that you will be needing to use regularly throughout the term, particularly on quizzes and exams. Because I will often present you problems which algebraically are going to be damn difficult. Third order, fourth order, fifth order equations. You try to solve problems like that with rigorous algebra, you've got a task in front of you. But there are easier ways to solve these problems. Let's take a look at an example of why that is true with this problem. Does equilibrium look familiar? We looked at it last time with the equation written in the other direction. Now, if we presume that we can operate at a temperature condition for which K for this expresses a function of concentration, K sub C is 1.0, then it wouldn't make any difference the direction in which we wrote this from a K value standpoint. It would still be 1.0. But if I looked at this with a K of 10, and I turn it around and the K value is 1 over 10. We've done this already. But, as I said, I like to keep the numbers as simple as possible when we first tackle problems like this, so that you do not lose sight of the chemistry. Because if you get the chemistry, you can always tackle the problem successfully. That's all you want. All right, I got KC written. We're imagining to deal with conditions that allow us this very simple KC value. I really doubt that that's achievable, but I don't care about that. And I'm presuming to study this system in a piston cylinder device. Certainly you talked about gas systems contained in a piston cylinder device in 2045. You own a piston cylinder device? Do you own a piston cylinder device? Yes. Do you have a car? Yes. Is it a Mazda? No? Then you own a piston cylinder device. In this piston cylinder, let's imagine that I've adjusted the piston so that I've got an internal volume of 1.0 liters. If M2 and H2 molarities are equal, and both 1.0, what's the ammonia molarity? Oh, that was tough. Which is why I was able to write, under these conditions, I've got a mole of each gas. Expressing this in 2C. Now we're going to apply a change to the system. I'm going to take a hold of the handle on the piston and shove it into the piston until I've reduced the volume to 0.50 liters, and then I'm going to lock the piston in place. The system, under these conditions, was at equilibrium. Under these conditions, is the system now at equilibrium? No. That means, in order to get us back to equilibrium, as Le Chatelier's beautiful, brilliant principle tells us. What does Le Chatelier's principle tell us? You read about that in the Chit Chat or chapter 17 in the note. Simply put, Le Chatelier stated that since equilibrium is the most stable thermodynamic state in which a reaction system can exist, if you do something to upset equilibrium, cause the system to become non-equilibrium. If at all possible, a reaction will take place inside the system to do what? Do what? Get us back to equilibrium. That's the most stable state the system can be in. So we're going to ask the question, after applying this change, what reaction must take place to get us back to equilibrium? Now, I haven't added any other materials. So the only possible reactions which can take place after applying this change to this system is it's going to react this way or it's going to react that way. So the only two possible changes. And it's our job to determine why. Now, there is a consideration that's also in the discussion for Chapter 17 in the notes about reaction quotient, symbolized with this squiggly fancy cube over here. Reaction quotient has exactly the same form as the equilibrium constant. But the equilibrium constant pays attention exclusively to equilibrium values for the components of the equilibrium constant expression. Molarities for solute species are all equilibrium concentrations. Partial pressures for any gases contained within are equilibrium partial pressures. Reaction quotient can contain any value. But it can be used, this reaction quotient, to predict, after, for example, upsetting the equilibrium system, like we just did, to predict what reaction will occur to get us back to equilibrium. Now let's make a decision on which of these reactions will occur based on this change without the reaction quotient. And we'll use the reaction quotient. It's discussed in Chapter 17. I'm kind of curious about whether or not you read this. It's your job to read it. The reverse reaction is the reaction which will take place to get us back to equilibrium. But why? Yes?
Since the reactant side has less relative moles.
Mm-hmm. Do you realize as this reaction goes right to left, as this reaction goes right to left, reverse of the way it's written on the form, you're going from more moles to fewer moles? If you have only reactants using the coefficients for the materials involved in the equation for the equilibrium reaction, using the coefficients to represent moles. If you have only reactants, you've got 2 moles of particles. If you've got only products, you've got 4 moles of particles. And when I reduce the volume, do you think that's going to drive the system to go from more moles to fewer moles? By reducing the volume? Sure. But if I up the volume, then I have a tendency to go from fewer moles to more moles. If I up the volume, I'll tend to go this way. But I reduce the volume. So at a glance for a gas-phase system, once you change volume, You can predict which way this thing is going to go to get you back to equilibrium. Increase the pressure, reduce the volume, more moles to fewer moles. Reduce the pressure, increase the volume, fewer moles to more moles. Does Q tell us that? Here's what we got for Q. We started with a mole of each gas. And after we applied the change, the volume was reduced from 1.0 liters to 0.50 liters. So I simply put those values in for the Q concentrations. And I see what kind of number I get relative to K. I don't have to do anything fancy with this expression to see that whatever the numerical value is for this expression, it's bigger than K. That tells me it's got to go this way in order for Q to get smaller until it becomes equal to K. But we're back to equilibrium. Okay. So, next directive. At this point, I have to tackle the problem algebraically. The rule of the road for tackling any such problem equilibrium, for any such equilibrium problem, the rule of the road for tackling any such equilibrium problem algebraically, or to put it from an ice table standpoint, to get at the C part, the change part, is to use the equation for the reaction as your algebra guide. See the equation for the reaction? So I'm going to say, since I have a coefficient of 1 in front of nitrogen, and I recognize this thing is going right to left to get the equilibrium, that X will represent moles of nitrogen, which has got to disappear to get us back to equilibrium. Well then, that guarantees, because that thing tells me, as I go right to left, for every mole of nitrogen consumed, I use simultaneously 3 moles of hydrogen. So if I'm going to use X moles of nitrogen to get me back to equilibrium, I've got to use 3X moles of hydrogen. I'm using these coefficients as my algebra guide. That's the easy way to do it, which tells me I'm getting to equilibrium. I will have, in addition to the 1.0 moles of ammonia originally in the system, manufactured 2X moles of ammonia, giving me this as the equilibrium mole quantity for ammonia. Now I've got to pay attention to something else. Once I've changed the volume to something other than 1 liter, concentrations and mole quantities no longer are numerically equivalent. Moles and molar concentrations were exactly equal numerically when I had a 1 liter volume. But now I got half liter volume. And the equilibrium constant expression is written in terms of concentrations. So I can't operate with mole quantities to solve this puzzle. I've got to get concentrations. So I'll take every one of these mole quantities, divided by the new system volume, leaving out liters just to not get messed up with units, which in this case we won't need. To get this as the molar concentration for nitrogen when equilibrium is reestablished. Molar concentration of hydrogen when equilibrium is reestablished, molar concentration for ammonia when equilibrium is reestablished. And I take these values now and I put them into my Kc expression, because the value for Kc is not changed. What I want to do now is to calculate the molar concentrations or mole quantities, either one will solve the puzzle, for each system component when I'm back in equilibrium. So I wrote this question. Because here's the expression we now have algebraically. How do we solve this thing? You want to take this and expand it? You're going to have one hell of a mess in the numerator. How do we solve it? Well, you reach for your calculator. Which one? This one. And you recognize that it's absolutely impossible to have negative or 0 concentrations in an equilibrium system. Do you agree with that? How tall are you? -3. The hell does that mean? This is an algebra class. This is chemistry class. We are materialists. Materialists of the highest order. materialistically revered, admired. I learned from. Because all the world was a big pile of chemistry, just like you are. Any living system is a marvelous, absolutely fascinating, astonishing assembly of chemical reactions proceeding simultaneously so as to, at least for the living system in question, maintain the healthy integrity of that living system. We spend our lives fighting against getting to what condition? Equilibrium! When we're in equilibrium, the game's over. So we do everything we can to prevent ourselves from getting to equilibrium. How are we going to solve this? I repeat, concentrations cannot be zero or negative. And now I ask you to examine this expression and let it talk to you. Which of these terms, molar concentration, nitrogen, hydrogen, ammonia, which of these terms is the smallest? Nitrogen, hydrogen, ammonia concentration. Which term is the smallest? Guaranteed. Hydrogen. Look at this. When I look at this, I'm letting this thing talk to me, I see at a glance that X cannot be larger than what number? X greater than 0, but not greater than what number? 0.33. You hear that? Because if X is bigger than this number, this term is negative. And that ain't possible. So I haven't done anything fancy. I've let this thing talk to me. And I already know that the correct value for X for this puzzle is in this 0 to 0.33 range. And I'm limiting my work to 2 sig figs, because the equilibrium constant is expressed only in 2 sig figs. The mole quantity is 2 sig figs. All right. Now what do? We speculate on a value for X, a simple value for X, to give us an idea about the correct value for X. Because I'm speculating for a value for X that's easy to deal with. I plot that number in here, I do the indicated arithmetic, and I see if I get a number that's bigger or smaller than 1.0. And then I know how to adjust X for my next trial, my next speculation on what the correct value is for X. Give me a simple value for X. Try X equals. What do I write in here? 3? You can write 3. How about this? That's pretty simple. Now let's put this test value in. This becomes 1.8. This becomes 1.4. This becomes 2.4. So now I have this. Now the pocket calculator comes in handy. I submit this information to my pocket calculator. And on so doing, let's see what I get. I get 0.86. Based on a test value of 0.10 for X, I get for Q 0.86. This test tells me, since 0.86 is kind of close to 1.0 in it, then I almost got the right value. But I now can decide that the correct value for X is either a little bit smaller or a little bit bigger than 0.10. How do you vote? A little bit smaller. Because this thing tells me. I'm letting this thing talk to me. And this thing tells me, as X gets bigger, this term gets smaller. Right? Because I'm subtracting in the top and adding in the bottom. And I got a number that's a little bit smaller than KC. So I got to have, as a correct value for X, a number that's a little bit smaller than 0.10. Prime X equals 0.08. I'm going to tell you to try this. It's 10% small. Now, when you try, I'm going to write this stuff down. At X equals 0.090, Q is equal to, let's see, 1.017. And you might say, that's right, because the 2 sig figs, that is 1.0. What if I try X 0.091, then I get Q equals 0.9999. And this, the 2 significant figures, is also 1.0. So one of these is the correct value for X. Which one of these is really closer to 1.0? Is it this? Or is it this? Yeah, that's it. And now you know how to do it. And that's the way you're going to want to solve these types of problems always. Because it's the only way to do it in a short, time-efficient fashion. Now, what you're going to do tomorrow in discussion class, and I didn't get at it, is you're going to start with Chapter 18 on Bronsted-Lawrence acid-base chemistry, which is damn important because all the important chemical reactions in our system to keep us happy and healthy depend someplace along the line on pH. Please, just about all the reactions. Read this stuff before tomorrow.